and Panama and Japan, and we're gonna
and Slovenia.
And Slovenia, yeah, represent. And we are going to officially start the first PIF remote workshop, starring Andrew Quitmeyer from fucking Dynacon, yeah. Sorry.
Yeah.
So I'm super excited about this one. We're gonna build some wearable ant farms, if you know what I mean. So the words is yours.
Okay, cool. Hey everybody, we got everybody here. I'm gonna share my screen and also talk to y'all about stuff while I'm sharing it. You can see my screen right now and you can hear me talking and see me like I'm motioning and picking up things, right? That's all good? Perfect. Okay, cool. So I'm just gonna keep talking. Feel free to unmute or barge in at any point in time. I have a little intro about what we do at Dinalab. So I think most of the people around here have been to Dinalab or have been to Dynacon or they're joining, but I'll try to just make it quick and brief anyway. So I'm Andy. I run this place called Digital Naturalism Laboratories in Panama, where we look at art and technology for interacting with nature in the wild. That's kind of our goal. Right now, we're based right next to a fun, fancy scientific organization called the Smithsonian Tropical Research Institute here in Gamboa, Panama. And we have our own little independent center called Dinalab, where we have lots of these little cute things called agoutis running around in our backyards, who are very nice and eat all of our garbage and bio waste, and they're very playful and fun. It's basically an old canal worker house. We've turned into a laboratory with laser cutters, 3D printers, workshop spaces, a little art science gallery, and a backyard and jungle trucks, and we have access to fun rainforests and all kinds of different things. We do field courses, and then we also have a long and short-term residency program, though right now that's a little bit interrupted. And so all of our previous residents have all left right now. So we're just kind of fixing up the lab and kind of enjoying the peace and quiet for a little bit until undetermined amount of time. Also, we're coming at you from Panama, which unfortunately is like number 3 in the world for infections per capita. And we've really blown up and it's really sucky. And we've also been under a really stupid gender ban lockdown, where basically if you're male, you're only allowed to go out on Tuesdays and Thursdays for 2 hours outside of your house. And if you're female, you're allowed to go out Mondays, Wednesdays, or Fridays, and then the weekends are banned. This has been going on since March. So it's been like 5 months of pretty much total lockdown. And if you're trans, it's complete lockdown for you and you're just fucked. So things aren't that great in Panama that way, but we managed to sneak out and have fun with ants and stuff. We'll do things like hiking hacks, outdoor workshops, and also like animal enrichment. So a lot of the projects we do try to focus on digital interactive technology and how we can kind of study animal behavior or probe animal behavior with these. So this was a project we did at the Singapore Zoo with the red pandas and the sun bears. And now we're working with a tapir and a spider monkey and an ocelot at a nearby animal rescue center. We also run a thing called Dynacon. Lots of y'all have been to Dynacon. Woo, yay! And it was inspired by PIFcamp awesomeness. And it's a big, long format, 100+ people kind of joining, flowing in and out in a semi-remote location for like 4 to 6 weeks. We had one in Thailand. We had one here in Panama last year, and then Dynacon 3. It was scheduled to be a couple different spots. Not really sure what's going to happen with that now, but stay tuned. If you're interested, you can always go to dynacon.org/contact and hop on our mailing list and find out whenever the next Dynacon will be. But what we're here for today is we're talking about ant tracking. And ant tracking is kind of my baby. It's a really profound challenge that we've had to deal with for, I've been working on this problem for 10 years now, which is bonkers. And this is what kind of got me started in this like tech meets art and science kind of world. So I was working in a lab that was a robotics lab collaborating with some people studying some ants. So this is an example of some of the ants. My buddy Peter Marting. You can see there's a big queen ant inside this tree called the Cecropia tree, which is kind of like a bamboo tree. You see them all over Panama. They have a mutualism with the tree where the ants live inside. This is a cross section of the tree. And the ants live inside the bamboo-like chambers. And then if something disturbs the tree, like a sloth crawling up it or leafcutter ants coming to steal the leaves, the ants spill out like a living force field and just start shredding and killing everything. They're called Azteca warrior ants. And they're really badass, awesome ants. And so we were trying to help study these ants. And one of the huge goals for people working with small animals is figuring out how to track them somehow. And so we originally I was working on computer vision stuff for ant tracking. We would sit inside a little climate controlled laboratory and we would program stuff and use some OpenCV, and we can make awesome stuff. It goes like, oh, I know where Susie ant is chatting with Sally the ant for 3.8 seconds near the watering hole, and then she goes and talks to Henrietta the ant, and it's great. So this works really good in the lab. And so me and my buddy Peter were like, well, hey, he's studying these ants out in the rainforest here in Panama. Let's go check it out. Let's set up his cameras and do everything that we do in the lab. And it gets complicated. And oh my God, everything fails. It totally sucks in the wild because of lots of reasons. And I'll get to those in a second. But one of the main things, and this is what drove me towards what I do. You know, if this was a superhero kind of thing, this is where I would be like the villain who's been twisted by this horrible problem and like vowed to one day track all the ants in the world. Because it really hurt me a lot to feel like we were really failing a lot of these field biologists. We would basically be like, oh, okay, our stuff doesn't work outside, so go grab all your ants and work inside, and make all of your experimental outdoor research indoor laboratory research, which is kind of the opposite. And unfortunately, you see a lot of that in any kind of like technology field where there's technology that has all these huge promises. Oh, we're going to do everything for you the best. But then it's like, okay, but you have to take everything that you like about life and bend it and break it so that it fits the mold of this, whatever the technology can do, which is shitty. We should be bending the technology to our will and not letting the technology crush and destroy us in order to fit its mold. So part of my goal for the past 10 years has been modular ant sensors. This is in comparison to what I would call the previous approach, the one big camera approach. So a lot of scientists, they want the one big camera because they want really high resolution details of these ants. They want all of these different details and, oh, this ant's talking to this ant for this long. And a lot of this comes out of a lot of laboratory studies, the type of data that you want. You run into problems though, because unlike in the lab where you have a flat, well-lit, gridded out space that's two-dimensional, the actual world is not two-dimensional. And like trees curve and ants walk on multiple, leaves and stuff. And so when you're pointing a camera at something, you're maybe at best seeing a third of the tree branch that these ants could possibly be moving around, and much less if there's leaves or other things in the way. So we would have to set up these ridiculous arrays where we'd have like $3,000 and up cameras, all trying to monitor one little spot. So we have like $3,000 looking at one piece of a tree, maybe this big around, and then the software would still kind of fail. So $3,000 for one spot wouldn't work that great. And then there'd be things like, oh, it's very bright out in the tropics, and so we would have to put up an umbrella to keep the light from like brightening out everything too much and causing too much shadows, and then also because the light shifts because the canopy moves around, and so you have changes in light that throw off all the computer vision algorithms, and then you're blocking it off to have controlled lighting. So then you have to add more lighting underneath it. So now you suddenly have all this extra light and all this battery power. So like your whole rig, you're up to like $5,000 for, again, trying to look at what's going on one little, like, let's say 1 centimeter strip of a tree and just trying to see what's going on. And for us and a lot of the ecologists, they're maybe not as interested in just this one little chunk of the tree. They're maybe interested in the ecology of the tree. So instead of this one little chunk of the tree, what's happening throughout the day as the ant traffic flows among the tree branches or down to the roots or along foraging paths? How does all of this change and develop in ways that's much more interesting than maybe one little node of the tree? You can think about it like when like there's city planners who have things like traffic sensors. You can have a whole city, and we're trying to make scientific inferences off of like one person sitting on the side of one road in like New York City and being like, yeah, there's a car there, I think. Or no cars, guess nobody's at home in the city. And so it'd be much more interesting to have maybe many small sensors scattered throughout the whole tree, able to monitor what's going on in this tree. Now the trade-off is going to be, it's going to be lower resolution data. You're probably not going to be able to tell the exact orientation and leg movements of maybe a single ant, and if it's talking to this other particular ant or whatever. But that's kind of we're trying to change what our goals are here. So instead of this ridiculously high precision over very small areas of ant tracking, we're trying to do something very simple that just says, is there an ant or isn't there an ant? So ant, no ant. So that's the kind of resolution we're looking for, but distributed over large parts of the tree. So very basic difference detection, ant, no ant. Some of these pros and cons, like I was talking about, if you have the one big camera, it's expensive. You can only look at one spot. It makes the world two-dimensional. It completely ignores this geometry. You have to usually do a lot of post-processing work too. So a thing that made me really feel very bad is because our lab, this robotics lab, was working on this computer vision tracking software, there would be scientists who would be like, oh, we can track ants. They would go spend 4 months getting terabytes of video footage because they anticipated like, oh yeah, I'll just collect all this and then we'll run it through software. Everything will be good. They get back and we're like, oh no, our software doesn't work on that. You need better lighting. And so like, unfortunately, on the tech people would be like, nah, go back and redo it, please. And they're like, what? I can't. So instead, for instance, my buddy Peter, he had to get like something like 20 different undergrad interns that they hired in the lab to just go through frame by frame of all these videos and just track all the ants manually. So like a lot of tech projects, it ends up just being a bunch of human Wizard of Oz kind of approaches. And that sucks. And so there's these people getting caught up in these magic fantasies of technology. And sometimes it has too much data and you don't even know what to really do with it or how to pull out just the little bits of data you want. As compared to kind of the approach we're looking at now, cheap. Let's figure out some way to get $1 sensors instead of $5,000 sensors on these little 1 centimeter strips all over the tree. Let's get many spots. Let's get real-time feedback. So we should have a little device that like we can test, set up in the wild, watch some ants go by and be like, yeah, this is working. This is awesome, great. And then if something breaks, we can bend it, we can resolder it together, or we can fix it while we're out in the field. Or we could, you know, curve it or change its designs to fit with the different types of tubing that are only available in Panama, or this weird shaped tree that we're trying to connect to. So those are kind of our challenges. Some other challenges we're gonna have with this is mounting. How do you get something on a tree that's not going to interfere with the ants? For instance, we bolted some of these little sensors into some trees, and the ants spent all day just attacking the sensors. They fucking hated it. So instead of it being an ant detector, it was more of an ant attractor, and they wouldn't walk in front of the sensors at all. They would just start attacking where it was attached. And so that was not great. But then after a while, so one solution is just acclimatization. So after a while, the ants started leaving it alone. So that's good. One of our biggest problems with ant sensors, and whenever people talk about a lot of technology, most technology is super human oriented. Every, you know, like sensor or whatever you're usually getting from SparkFun or Adafruit or whatever, it's usually oriented for humans. We're very self-centered species. And so you get something like, oh, this is a heartbeat detector for humans. So there's always the parentheses for humans and basically every type of sensor that you ever get. And this would be okay if ants were the size of humans and roughly our same configuration as humans. And I would be just enthralled anyway, because we have giant humanoid ants walking all over the place. Unfortunately, though, ants are very small. And they're not only very small, they actually are a huge range of sizes, too. So ants really exhibit a huge amount of polymorphism. They're a bigger range of things to potentially try to sense than like a blue whale versus a human. There's ants that are comparatively bigger and smaller than like a blue whale is to a human. So you can imagine like for every sensor, like if all of our face detectors only worked on blue whales and then we tried to use them for little humans walking around, that's the kind of challenge that we're dealing with. Even within a single species, within a single colony of ants. For instance, I'm using the leafcutter ants. They're the most prevalent around here, but they're not even necessarily the most polymorphic. But they'll have a huge, like 100 to 1, sometimes even 1,000 to 1 size ratio of ant sizes. So try to imagine making a sensor that can work on something that's you know, human size and then 100 human size at the same time. So that's incredibly tricky, and they're very, very small. So you would, this is from previous work of just testing out some of the ants I could collect. And so I had like one sensor that could work on a large leafcutter ant, but it couldn't work on a medium leafcutter ant. I had a different sensor that we were making out of graphene and silly putty once, and it looked promising, but it can only detect the footsteps of a medium-sized angry leafcutter ant. And so if it was chill and relaxed and walking around on it, you couldn't even detect it at all. So it was only if I angered it first would it actually work. And so it's really tricky, and it's taken a lot of evaluation. I'm just going to go through some of the approaches that we've tried. So one of the most common things for looking at insects right now, like the current state of the art pretty much still is computer vision or IR photogates. So computer vision, we talked about a little bit. It's very good for especially if you need one view, one spot, get very high resolution imagery there. But a lot of cameras are still too expensive to just put everywhere. Then there's IR photogates. They use this a lot for honeybees. So honeybee detection is actually quite well done because you can basically just have these photogates. You have a sensor and then you have an emitter. And basically when you have bee and then you have tubes, that go to your beehive, and the bees know exactly where they're going home, and the bees are very comfortable living in this kind of artificial area. And so the bees can walk right through, and you can even get things like if you have sets of these Photogates, you can tell if the bees are coming or leaving based by which sensor gets triggered first when something passes through. And so you can have pretty good sensing for bees, and there's scientists and bee farmers who have really great data on, you can see like, at 6 a.m. the sun came up and all the bees flew out, and then they came in for a siesta when it got too hot, and then they flew back out. And so you can get really good data on those. But you have a very controlled environment, and bees are chubby. Bees are thick boys, and especially compared to ants. We tend to, even I at sometimes will think like, oh yeah, we can totally sense bees. That means we can sense ants. But ants are very thin, and I haven't seen a Photogate detector like this that can really work on most ants, other than like a bullet ant, which is a huge ant, but we're not as concerned with that one. It's not as common either. But most size ants aren't really going to get picked up by just your regular IR Photogate. And so instead, so a nice thing about Photogates is it's cheap, but it's not sensitive enough, and you need to really control the geometry. The insect has to really walk through a very specific area. So then there's other things that I tried out. I tried little high resolution rangefinders. These VCNL 4000s are pretty great. They have resolutions that can read in like the tenths of millimeters with quite good accuracy. The problem is that their target zone is basically a dot. So I can tell you if an ant walks by anywhere on this fake tree that I have here, as long as it walks by that exact dot. So again, not really solving our problem there. They're like 14 bucks each. That could possibly be doable. Thermal, that was a big goal of like, oh man, maybe they're not showing up for computer vision, but we can just do like heat sensing or something. This works really good for bees. This is my buddy Barrett Klein. Again, lots of technology works for bees. One of the reasons this works for bees is bees fly around a lot and they get really hot. Ants are actually just pretty cold. They're very tiny and they're very cold. They only fly when the queens do a mating flight, but then they land and they rip off their wings and they go, I'll never fly again. And they set up a whole new colony. And so they never fly and they never get hot enough for pretty much any thermal sensor to really detect them above ambient temperature. So thermal's not really working great. There's electric field sensing. I like this because I basically like turning things into theremins, and I love capacitive touch sensing. It's one of the easiest ways to make anything interactive. So I was hoping like maybe, and it's very cheap too. Usually it just involves some, making a very simple kind of radio and just some metal that you bend into a shape, and then you could see if something interferes with this electrical field that you send out. Unfortunately, it works good for humans, frogs, even large grasshoppers. But ants, too small, too dry. Most of this kind of electric field interference really needs some kind of wetness, some moisture, something that'll interfere with these electrical radio waves going by. But the ants is really, really not working. This is something that's vibratory. So picking up the sounds of ants moving around. This is probably the thing that's worked the best, and especially like the bio art world. So there's people like Kwai Shen and people, I forget, I'm blanking on her name right now, Lisa Schoenberg, who was just at Dynacon last year and does lots of recording of ants. And basically you can use a piezo element that lots of people are probably pretty familiar with in general. Basically little microphones, surface detecting microphones, and you can pick up the sounds of ants walking on top of them pretty well. The downside to this though is that the ants have to walk on the microphone. So you could, and then often these are kind of rigid and they're hard to like mount on things, and the ants don't readily walk on a lot of these surfaces. We even tried putting other surfaces and attaching the mics to that, but then a lot of the problem becomes there's just too much other ambient noise. It doesn't become that good of a reliable ant detector. So they're pretty good for like sonifying ants if you have them in like an ant farm and you want to hook them up to a synth and make some cool noise music. But scientifically, they're not as, I haven't found them to be as reliable so far. They're noisy. It might hinder ant walkways. One thing we almost had good luck with is optical motion detection. So a lot of your computer mice have driven the development of basically what are really high-speed cameras that are very low resolution. So all of your optical mice have a little camera in them. It can be, this was some really cheap ones. They were 18 by 18 pixels. Most modern ones now are maybe like 64 by 64 pixels, and they do like 3,000 to like 10,000 frames per second. So they can get stuff moving by very quickly, and they're used to, you know, basically detect the surface and very slight differences happening as it moves across something. And they're extremely cheap. Some of the main problems are, and so you can actually even turn it into like a slight camera a little bit. But some of the problems with them are they're pretty locked up. So a lot of the decent ones, they're basically, they have proprietary firmware on them, and you're not allowed to hack into the things that'll actually give you the data from them unless you sign this like NDA with the companies. On top of that, all of these cameras are set up with lenses that are basically just supposed to read at exactly where the camera is. So it's like an extreme macro lens. So I was trying out a lot of different custom lenses because we would need to see a spot, maybe like a 10 centimeter spot or something. We make a ring of these monitoring any kind of movement. But lens making is tricky. And it started making the cost of this like $1 sensor a bit more expensive. And it was just too much of a mess to hack, and I couldn't really get that decent of data from it. Folks at Hackteria have been trying to hack these for a while too. So it remains kind of a goal that I think a lot of people could do a lot of really cool stuff with, but it's unfortunately a kind of locked up, messy technology right now. So that was most of the things we were trying, and it was like, oh, this sucks. How are we ever gonna sense ants cheaply in distributed areas around? And so more recently, like in the past couple months, I'm like, okay, well, I've tried, you know, all kinds of different surface stuff. I even tried this, making this graphene silly putty. I didn't include a slide about that. And that worked good for angry ants, but not other ants, and it had other problems too. But so it made me, I was starting to think about light some more, and just doing any kind of like, can I get anything from just reflected lights? And for this workshop, we're going to focus on, instead of entirely wild ants, maybe ants inside, you know, little ant farms that we make that we then can turn wearable, so we can control the environment more, and maybe have something a bit more like with the honeybees, where you could have little photogates. And so, for instance, you could just hook up a regular, you know, very basic Arduino project. You have some LEDs somewhere, and you have some photoresistors. So this is like, you know, an Arduino 101 project, like, can we sense light? And it turns out you can sense light pretty well. But again, each one of these photoresistors is about the size, it's larger than most of the ants we have around. And so even if there's an ant walking directly on top of this photoresistor, the sensitivity isn't that great. And especially because ants are so skinny and they have their little legs, the light kind of bounces and bends around them quite well. So they weren't really doing very good for picking up light or for picking up ants and the subtle changes in light that come with the ants. Plus you have all kinds of like ambient light interference that's a little bit tricky. But then I was like, well, what if we just get a lot more fancy with how we're doing this light sensing. So instead of like, there's light on this side and there's a sensor on this side, and we just see if they break the gate, what if we do something like we have an array of lights over here? And so we turn this light on. So first we measure all the light and we get like an ambient light reading in general. So we know what it just looks like with just normal daylight happening. Then very quickly, we turn on one light, and then we take a reading from this sensor and this sensor and this sensor and this sensor. And then we turn on another light, and we take a reading from all the sensors. Then we turn on another light, and we take a reading from the sensors. And then we have a light maybe up here at an angle, and we take a reading from that light. And so we take, like, let's say 10 readings from different light sources, bouncing around over and over again very rapidly. And it'd be like, for example, if you have me right here being lit kind of ambient light, and then having this ring light over here, and then having another light over here, you would be able to capture a much more high resolution concept of what might be very slight changes in light happening. And so this is kind of what they call like modulated light sensing. So we basically have lots of LEDs around, and they're lighting up the ant from many different points of views. And the goal is that if we accumulate all these slight differences in light sensing, we can very accurately know if there's something there or not. And it turns out that actually works pretty well. So I just rigged up this simple array earlier with the lights and these little photoresistors, and it started working, and we could detect ants walking by, even if they weren't walking directly in front of the sensor, because even if they were walking on the side, they might cast a shadow from one little LED over here that's doing something. And it turned out it could be very sensitive that way and very resistant to ambient light changes. So that was great. I'm like, okay, cool. Let's do this for PIFcamp. We're gonna have photosensors and lights, and we're gonna have strobing LEDs all over that are shining at the ants, and we can sense them. That's great. But then while I was preparing the workshop, I was like, okay, but you know, sometimes like not everybody has like a photoresistor. It's a pretty standard part, but it's not always the most common in anyone's kind of like kit. So there's another process you can do where you just use 2 LEDs. So you can see that on my screen right here. What you can do is all LEDs, if you pass electricity through them in one direction, they shoot light out. But one thing that's kind of cool is that when you shine light on an LED, it actually charges up in the reverse. So it can provide a it's like a very crappy solar panel. Unfortunately, if you plug solar panels in reverse, they don't beam light out. That would be pretty cool. So in some ways, LEDs are cooler than solar panels. But so you can use an LED as a sensor if you just plug it in reverse style and plug it into the inputs on your Arduino. So that's pretty neat and spiffy. And so the problem is that if you use the LEDs in reverse, they are much lower sensitivity than like these photosensors that we were using earlier. These are dedicated and made to sense light. These LEDs can sense light, but they don't do that good of a job about it. And so I was like, okay, well, I'll make some code that'll be backup in case somebody just wants to play around with light sensing in general. And so I made that code, and it was fine. But then I had some very tiny LEDs. These, if you're not that familiar with LEDs, these are called SMD LEDs. And they're the kind of LEDs that are soldered directly into things, and they're very small. Let's see, where is it? It's just this little dot right here. It looks like a little blob of solder. There, right up there. So that's a full LED. It's just a very tiny LED. And so I was like, I had this thought like, okay, well, if I have the code for the LED sensing anyway, maybe even if they're very not sensitive, they're small enough, and we could just pack like, 20 of them in the space that, or maybe like 5 of them in the space of one regular sized LED, and maybe that'll increase the sensitivity a little bit. It turns out these red SMD LEDs are actually very sensitive to light changes in general, much more sensitive than the red LEDs themselves, and they're also very sensitive to the lights that they emit, which gave me some ideas. So then what we can do, and they're extremely cheap. So they're small, very cheap. You can get, a roll of them for like, they come in little strips like this, just to try to organize them. But you could pack a regular board of these with just tons and tons of little tiny LEDs. And on top of that, you no longer have to have separate LEDs lighting up your scene and sensors. Instead, every LED that you have connected to your Arduino can also be a sensor, and then can also help illuminate the other sensors. So for instance, and we'll go over more of this in the workshop tomorrow, but let me restart this. There's the reset button. So this just has 3 of them on there, and it'll go kind of slow at the beginning. So each of them, it looks like they're kind of strobing right now, but they're going extremely fast, and they're lighting up different areas of whatever they're trying to illuminate. And in between each illumination, they are also recording the light of all the shifting lights of all the other LEDs. They're doing this extremely fast, every couple microseconds. And so what we can do is I made some 3D printed little hose grabbers. And so this is, here we go. So this is just a tiny little PCB with 3 of them on there. And so then every time an ant walks by, I don't know if the ants are coming out right now, but it can actually illuminate the ant from several different directions, and then be able to very reliably tell if an ant's there or not, which is super cool. And so that was really good, really nice finding, and that we can basically make a ton of these very high sensitivity LED sensor arrays that are modulating and strobing the scene in many different ways, several hundred times per second. This is called reverse biasing an LED. It's super cheap. It was too insensitive to do with regular size LED, but with SMD LED arrays, it's working great. So we can think about, you have the regular Photogate, but then we went to this SMD array where maybe instead of just 1 sensor in the size of an ant, you have 3 sensors illuminating the ant from many different angles and areas, and able to tell all those slight differences as it moves on. And because these sensors are so small, geometry is not as much of a barrier for us. We can make like little rings or half pipes that we could set over an ant trail and have the ants walk underneath, and they'll be illuminated from the side as well as the top, and rapidly collecting this data and hopefully able to sense the ants passing by. Then my goal also could be, maybe we make a strip that's thin enough, because you can have these flexible electronic boards, put some of the LEDs on that, and have it thin enough and densely packed enough that just the ants could maybe just walk right over, won't even notice. Or we could have an elevated full 2 half pipes come together in rings around branches or trees or leaves or something like that, with a whole ring of these LEDs that then solves, in theory, our problem of, is there an ant there or is an ant not there in this ring somewhere? And so that's kind of the big scientific goals for right now. And this is an example of how we're calculating the different illumination patterns from each side of the LEDs, and we get really good responses. So this is an example of just some of our very early data of an ant kind of walking by a set of just 2 of the sensors illuminating each other, and this was actually at perpendicular angles. And you can see nothing's happening, and suddenly the ant walks by one sensor, it walks by the other sensor, and then it goes right past back the other sensor. It kind of walked in and out, and that was awesome. So We'll talk more about these sensors and we'll build some tomorrow. That's going to be great. And it shouldn't be that hard. It's basically just soldering SMD LEDs is probably the hardest part. They're very tiny, but it seems harder than it is. But other than that, you just have those, you just have some wires. Some people put, you know, like resistors in with their LEDs. They're like worried about stuff, but you don't even really need the resistors. It works. Just plug it into the Arduino. Live on the wild side. If you just want to get making some cool, funky ant synths, just LED right into the Arduino. It's fine. And so then you just plug them in. There's like no other hardware, no special capacitors or any kind of shit like that. You're just plugging weird little LEDs in a specific way into your Arduinos, loading up the code. I already made code for you. You put that in, and now suddenly, if something small passes in front of this, your thing will beep, or it'll detect, or it'll do whatever you want it to do. So that's the initial part of sensing. Let me just very quickly, in the time that I got left here, just kind of chat about the other parts of wearable ant farms. So first of all, how do you catch ants? You got ants outside. How are you going to catch them? First way, easiest way, hands down, simplest approach. If you see an ant, you can pick it up. Boom, you've caught an ant. You can put it in a tube if you want. Maybe you don't have something fancy. You put duct tape over the tube. You put duct tape over the other side. Now the ant just walks back and forth inside of the tube. You've made an ant farm. You're a genius. Okay, great. So that's the easiest way to make an ant farm right there. Now you want to get a little bit fancier. You're like, okay, well, that's just a worker. The worker is not like a real colony. It's going to walk back and forth and then eventually die. Fun fact, this is how all of the ant farms that were popularized in the 1950s, this is how they actually all were. It was just worker ants. And they actually use an ant called Camponotus barbatus or something, the harvester ant. Oh, hey, Marco's here. And one thing that sucks about these ants is they're one of the most painful ants that can sting you. But they were the ants they would ship to little kids all around the 50s because they were very, very robust workers who would walk around in the ant farm for like 3 months before they just died. They don't really need to really eat that much. They're not feeding a queen. They're not raising a colony. They just walk around until they die. That was the state of most ant farms, you know, that you think of when you think of like classic little kid USA ant farms. It's just captured workers that walk around until they die. The reason they were just workers is because they're not allowed to ship queen ants across state lines because they're worried about ants getting out and becoming invasive ants around the world. So you can just use a worker ant. It's not going to be like a full living organism. It's not going to be a whole colony, but you know, it works. Second easiest way to start your ant farm, you're like, I need a whole colony. I need it to reproduce and grow and show me all the majesty that is ant farms and ant colonies. So the second easiest way is you happen to wake up in the morning very early and you see all these big fat ants walking around with huge wings, and they're landing and they're like looking a little like worn out. That's because they just had a big mating flight and they all just landed after their big sky orgy. And the queen has all of the sperm that she's going to use for the rest of her life. And some of these queens can live for 20 years. They store it in a special pouch called a spermatheca, and they can inseminate all their eggs. They have like millions and millions of eggs throughout these 20 years of life with just this one mating session that they have. So anyway, they go up, they mate, they land, they have all their reproductive material they need. They're going to rip off their wings. They're going to dig a hole and start their new colony. If you see these ants walking around, you can pick them up. You can put them in a tube. After a while, they'll lay little baby ants. Maybe you'll want to hook that tube up to maybe some sugar water tube, and they can get a little sugar water. Maybe you chop up some mealworms or give them some Jello. This is what a lot of scientists, they give them gelatin. And then they get the protein from the gelatin. And then boom, you have a whole thriving ant colony. You might then want to start making your ant colony a little bigger because they're going to reproduce and get bigger and bigger. But there you have a whole colony started from one ant that you just picked up. So that's the second easiest way to start a whole colony. Just pick one up. It happens to be a queen that's already been impregnated. There's a very low survival rate of queens. Even in the wild, at least 90% of them are just going to die. They're going to like mate, they land, they dig a hole, maybe they lay their babies can't go forage enough food, and they just die. That's just kind of what happens. Okay, but now you're like, I don't want to wait. I need my whole colony right now. So this is what most of the scientists do. They do this method they call drip flotation method. And so what you do is you see some ants, like Simone saw all these ants. They're big and they're near the fire. He says he's a softie, but I see him later getting all into a shovel and just digging up some ants somewhere. So you can find a colony. You want to give the colony a good birth because you know it goes underground and then spreads out probably a little bit. And so you dig kind of a perimeter around the colony and you dig it all up and you toss it in a bucket. Okay, so now your whole colony, this might be several colonies that are very small, or it might be one colony that they dug up and they tossed into a bucket. Now, what you do is you slowly turn on a little hose and you just drip a little bit of water into this bucket of dirt and ants over the course of maybe like an hour, a very slow drip. So they're like, oh, hey, it's raining, but all of our irrigation routes that we dug underground, they're not working. We need to evacuate our nest. So they start evacuating, and then eventually they can combine together, and basically most ants can do this. They glob together and they can float around, and then you just scoop them off the top. You just scoop your little ants off, you put them in whatever container you want, and now you have a whole big ball of ants. They'll dry themselves off, that'll be fine, and you have a nice new captive ant colony. And then you just need to provide it basically with sugar and protein and decent humidity and temperature. Your ant farm's ready to go indefinitely. There's another version of this. This was with some bullet ants that we had in Panama. So this is the world's largest ant and most painful ant. And we used what we call the bucket and a lube bucket approach. You do this sometimes if your ant is maybe not underground. For instance, these ants were inside of a tree branch, so kind of like a log. And so their whole colony was in there. We got a really big bucket. We very quickly put on lots of protective gear, even though the ants could sting you right through it. It was mostly so that we were all uniform in color, so we would know if one of these big ants was on us. So we grab the log the ants are in, we smash it into the really big bucket so all the ants evacuate, and then when the ants walk up to the edge of this, we pick them off with tweezers or knock them into this lubricated bucket. So do you see this lower bucket down here? It has some white stuff around the edge. That white stuff you'll see in lots of science labs, and that's called fluon. It's a liquid Teflon. And so it's it's like basically like a Teflon coating like you have in your Teflon pan, but it's a liquid that you can apply to the edges of whatever, and then the ants can't walk up it. And so if you don't have fluon, you can also use things like WD-40 or motor oil, or not like motor oil might be too drippy, but 3-in-1 oil. So like thin lubricating sprays will make it so that the ants can't walk up it that much. And then you can have an open air ant farm that's also can be kind of useful. If you do have fluon, don't smoke anywhere near the fluon. The fumes combust and give you this kind of chemical pneumonia. So you'll be like, it'll like incinerate these little particles into your lungs if there's burning anywhere near the fluon, and it'll give you this pneumonia-like symptoms for like about a month or so. That's just purely chemical. So it's not that great of a substance. But if there's no fire on, it's very inert. The final way of capturing ants that you can try out is you can use other ants. So ants have very sophisticated social lives, especially in between other different types of species of ants. And sometimes you can grab ants from one place and then toss them in the other place, and the ants will be so scared of this other ant, and they'll think that there's a whole invasion, that they'll evacuate their whole colony. And then you can sit there with a little ant vacuum cleaner and just suck them up. So this is my friend Adrian Smith. There's these things called pooters, P-O-O-T-E-R. And if you saw me when I was at PIFcamp in 2017, I was going around sucking up all kinds of ants and some of those jerk wasps with this little one that you hook up to your mouth and you can suck it up. If you go to Thingiverse, there's people who have 3D printed insect sucker-uppers, also called pooters. Fun fact, they're called pooters, not because it's pretty much the perfect name for this thing. You kind of poot up these ants, but it's named after the scientist named like William Poot, which is a hilarious name. So they're just pooters. But so some people make really fancy pooters that hook up to vacuum cleaners. Then you don't have to suck them up with your mouth. You just go like, and it suck up a whole bunch. And so what this guy does is there's one kind of ant that's really scared of these army ants. He picks up like 3 or 4 of the army ants, tosses them down at the target ant colony. These ants go, oh my God, there's gonna be like 1 million army ants here in just a couple minutes. Everybody get out. And so they all run out, and then he just sits there with his vacuum cleaner and just sucks them right up. Super simple. So that's how to collect ants for an ant farm. But now, wearable ant farms. Okay, cool. Maybe we can send some ants. Maybe we can have some ants. Andy, why do you want to cover your whole body with ants? Valid question, I would say. Why are we wearing the ants? And also people are like for instance, you met a guy who's an ant farm enthusiast. And for ant farm enthusiasts, they're like, oh, the worst thing to do with an ant farm is to shake it around or move it around. Because it's going to disturb the whole colony. They're going to freak out and move around and not really exhibit their normal behaviors. Totally understand. Wearable ant farms, weird idea. So there's a couple reasons why I want to have ant farms all over me. One, it's really weird. 2, I want this kind of, a lot of my work is I want people to be able to experience ants and ant colonies in very different visceral kinds of ways than we normally see them, and people, you know, they never really get that close to them. And I experienced this a little bit. We were trying to make some ant sensors to monitor whole trees. We were in Madagascar with Hannah Perner-Wilson, and while we were putting these little fiber optic sensors around, a similar kind of idea. It didn't really work that well for a lot of the small ants. Some of the big ants it kind of worked, but we were trying to think of how do we share this information. And because we could have like a little light that turns on or a computer display, but then you're just busy looking at this computer display the whole time, and you're just focusing on just this one little part. Especially if you have a whole tree going on, how do you interpret this knowledge? And so I wanted something that would let me experience an ant colony in a kind of ambient, very visceral manner. So it's less like I'm getting more like pre or post-processed data that says like, oh, the ants were very active today all over or whatever. But instead, I want to like viscerally feel and develop my own innate understanding of like, oh, some clouds went by and suddenly there was a flurry of activity in the upper branches of the tree. In some ways, I want to kind of become the tree that the ants live in. And so I want to be able to feel the ants the way that their symbiote, which is normally the tree, perhaps feels the ant. And so I made some things like a little tongue display that just has little electrodes. So every time the ant will go over one area, it would zap a different part of my tongue. And so I kind of have a model of the tree on my tongue, electrocuting my tongue. So that's like one possible way you can kind of wear the sensations of your ants. Another thing could be maybe we have these ant farms all over ourselves, and along with these sensors that we have rigged up, and they're hooked up to maybe little vibrating motors. And so we can kind of walk around, experience the day as we normally would, look at the sky, ponder life, and while at the same time be getting this kind of feedback as the ant colony similarly is doing these kinds of things. And so I've done other things like an ant tree meditation where I pissed off one of these trees that goes and has all the Azteca ants spill out and try to defend the tree. And I made a little thing that made it so that I would have to hold on to the tree or else I would get zapped. And so I was trying to like meditate. It was like a forced meditation while these ants were crawling all over me. And that kind of helped me feel a little bit more connected with the tree and also the rhythms of the ants as they came in the first wave, which is what you normally experience when you piss off some ants. But then the ants kind of chill out. But then the ants come back and start attacking again. And so the different kinds of waves and the daily movements, those were the kinds of things I was interested in learning about the colonies that people don't have really hardly any experience with. So meditating with these ants. And then possibly the final thing that I want is, this is kind of what I see as almost like my trick of the ants, of the wearable ant farm concept, is that a lot of people think it's about like mastering these ants and like, oh, I've captured you, the ants, and now I wear you around and you're my cool, oh, do you see my ant watch that plays synth sounds at PIFcamp? It's awesome. So I anticipate people doing that a little bit. And like, oh, I have this cool hat that hooks up to Bernard's lasers, and whenever the ants walk around, I shoot lasers out of my head as the ants move around. That's super cool. And so that's what I kind of see as like ants as accessories. So still in this kind of like human versus other creature relationship where we're the dominant thing and we have them for entertainment, entertain me ants, and we kind of learn about them. But then I wanted to start changing the people. So then you're like, oh, this ant farm watch is pretty cool, but what if I had like 20 ant farm watches? And I could feel them kind of moving up and down or how they interact with each other. And like, oh, you know, I was walking around a little too much and all my ants were freaking out. Maybe I'll just kind of walk a little bit more slowly today and, you know, take like 10 minutes to cross the backyard at PIFcamp and just see how the ants go. And so suddenly now you as the human are kind of becoming more like the tree. You're kind of trying to facilitate the ants. And this is kind of my goal. And then the eventual goal is the ants aren't even captive anymore. You are luring the ants in through your farms that you have mounted onto yourself, and then you almost embedded yourself into the anthill and just letting the ants course through you and flow through you throughout the days. And you have become a complete human ant cyborg symbiote, and you leave your humanity and your agency behind, and you are just part of the colony and you do its will. So that's why wearable ant farms. I'm trying to help the ants take over your bodily autonomy a little bit. If you're not as into putting ants on your body, that's okay. There's some other projects I've done before that I think people can also try to ring with. If you have sensors that can sense ants and you can put ants into some sort of captive area, you can make another kind of perverse concept, which is, you know, a regular cyborg is a cybernetic organism, but ants are a super organism, so you can make a super cyborg. And so you can make like a robotic ant colony. People do this all the time with like interactive plus animals, and there's like 50 different projects where there's like a goldfish in like a robot bowl, and the fish drives the robots around, because normally you're like from like a very basic, like, you know, kind of art interactive standpoint, you're like, fish are always still in aquariums. What if they could move? Crazy. And so you can do the same thing, but for a swarm. And so ants are normally stationary. They're glued to kind of a specific spot as an organism. They can walk around and do things on their own, but as an organism, they are locked down to where the queen has made her chamber. So what if you put the whole ant farm, though? You have sensors going out. there's holes small enough for the workers to go through, but the queen doesn't leave because all of her babies are there. And where the sensors go, it makes the robot drive around to different areas. And maybe it can be a very slow bot, a very slow robot, a slow bot. And it can slowly cruise around. And will the ants be able to understand these changes? Will they still be able to forage even as their whole colony slowly shifts around? Try it out. I was trying it out a couple of years ago, trying to use an optical approach. Didn't work that well, but did have an ant farm kind of driving around on some robot wheels. That was fun. I'm sure somebody can do that at PIFcamp. If Michael Candy was there, I 100% know he would be doing that. So, in short, it's PIFcamp. Here's a fun week of stuff with ants. What are things that you can do? You can catch ants. You can look at them. You can let them go. It's great. That's just fun right there, just looking at ants. You could make an ant farm with different sensors in it. Come for the workshop tomorrow. We'll put little sensors into the ant farms. We got 3D models. We can print them right up. It'll be great. If y'all don't have the plastic 3-inch squares to pop on the ant farms, you could probably just use like saran wrap or something like that too. You're crafty, you'll figure something out. Put clear tape and sheets or something. It'll work out. So you can make ant farms with sensors. You could make an ant farm synth. I'm gonna be incredibly disappointed if there's not at least one ant-based synthesizer that is going on at PIFcamp. I mean, come on, folks, where are we at? Then you can make an ant farm wearable. One thing, if you're printing your ant farms out of PLA, you could just hot glue that thing right onto a shirt. Oh, I got a wearable ant farm. Good for me. Maybe you could add some little actuators. You could have it buzz or beep or something. So then you can feel what the ants are doing connected to those sensors. Cool, interactive wearable ant farm. Maybe you don't want to put the ants on your body, make the ant farm mobile. And then at the end of the week, let's have an ant farm fashion show. And people can document their projects. We can open up the blog up at Dynacon, and people can make just like quick little WordPress entries if they want, or however we figure it out. We can just have a big Google Drive or something. But we can document all this, and it'll be great. Also, maybe the sensor, you don't have to use it for ants. Just scientifically, some other things that these little tiny insect detectors could be good for is when butterflies pupate. Often you don't know if they're like moving around yet. You could have very simple sensors when the slightest movement starts, so you can catch them right before they're going to be coming out. You can make little camera traps. So like put it on a tree, maybe the ant walks by and you take a little picture of it with a Raspberry Pi or something like that. Little ant camera trap. Or, you know, music generation of non-ant things. You could use it, you could stick your fingers in there. You could just play around with the sensors in general, make music out of it, shoot lasers. Yeah, and that's pretty much what I got for today. So let's chat about some questions or whatever people got, and we'll have a workshop tomorrow to build some things. Yay! I'm gonna stop that share, put on the chat in case there's any chats, and then, yeah, people have any questions? What about people over at PIFcamp? Y'all got anything?
I have a question. How long does an ant live if you don't move her or anything? Like, what's the approximate age?
It depends on the species of ant, and also the type of ant. So like workers, some workers might only live for like a couple weeks. So the ant life cycle is basically a queen lays an egg, the egg hatches into like a little larva, like a little grub, a little caterpillar. And then the grubs, for most ants, they're the ones that have chewing mouth parts. And the workers, they have like those kind of pincher mouth parts. Those are really just picking up stuff. They're kind of like forklifts. They can't really chew. So they have to pick up that food. They have to give it to little grubs. They grind it up, eat it, and then they puke out a liquid so that then the workers, they actually just have a little straw that comes out between those pinchers, and then they slurp up that liquid. And so the workers all live on puke from babies. So it's kind of a good way to make sure that your society is feeding the babies and the young, because they literally can't eat anything but baby puke, like secondhand baby puke. So yeah. And so the workers might live for like a couple weeks. Some workers might live up to like maybe a year or something like that. But then the queens, depending on the type of ant, they could live for a year, a couple years, or even like 20 years. We had one queen ant in our laboratory who was like 14 years old. And then one day she just went kind of senile and just walked out of the colony, and the workers kept dragging her back in, and then she just kept walking out, and then one day the workers just decapitated her. So they were through with monarchy.
What's the plan for tomorrow?
The plan for tomorrow? So I would like tomorrow, people, just if you have basic Arduinos and some SMD LEDs and some little perf boards that we could solder them to, that would be great. If we're lacking some of those materials, we can try to work around things. We can do things with just photo resistors, but I think it'll be the most fun with some SMD LEDs, some soldering, and some Arduinos, and we can turn them into sensors right away. And then people can just start playing with these arrays of sensors and doing whatever they want with them. Putting ants in front of them, hopefully, or doing whatever. So I think that's my main goal for tomorrow, is just making SMD LED sensors.
Yeah. Okay.
Cool.
And tomorrow at the same time?
Yeah.
Yeah.
This was
Perfect.
great.
Yeah.
Voila.
Voila. And tomorrow I think it's gonna be even greater.
Greater.
Perfect. Awesome. Well, thanks so much for hanging out, y'all. Y'all are the best. I miss y'all. I can't wait to be there next year. Hopefully, definitely.
Definitely.
Yeah.
All right. Hey, see you tomorrow.
See you tomorrow.
Cool. Bye.